So next topic up is 11.4, which is graphing in polar coordinates. Now we had a brief introduction to polar coordinates in the last lecture, and now we're going to work a little bit more on graphing. Now for Madison College students, who is, you make up the majority of people watching this video, surely, I already put a couple of the Patrick JMT videos up. And he does an excellent job showing the basics of graphing in polar coordinates. But I could not find one from Patrick that shows one of the most important topics. And what I believe to be, oops, that's not one. One of the most important topics should answer the question, why are we even bothering to do this stuff? Because we have calculators. So let's first do the traditional thing here and write graphing in polar coordinates. Might as well write it out. And so Patrick does a good job of making a table of values, so filling in the lines, kind of thinking through it like that. So we'll address right away, why bother? Because I have a, I don't know what the latest is, TI 97 Gold Plus, whatever, calculator. And the answer is symmetry. We want to learn to recognize symmetry. Just like when you're graphing parabolas in your algebra class or whatever class you did that, you really only had to do half the parabola because you knew what the other half looked like. Well, we're going to do the same thing now, except in polar coordinates. Let's look at a couple of really easy examples of some equations in polar coordinates. One is, let's say I just want to graph r equals 6. Well, what does that look like? I remember that the graph, and I always try to convince my college math students of this. That's not very good. I'm going to center this. And it'll work out better in the long run anyway. A graph is just a picture of all the points that work. So if I say r equals 6, doesn't depend on theta. So I just say, okay, well, here's 3, 6, like this. And so I'm just going to have a bunch of points that all fit the relationship r equals 6. Not much of a relationship. So it's just going to be a circle. Right. Another one could be another easy one. That's supposed to be easy. Is our how about, let's just set theta. It doesn't depend on r. Theta equals pi over 4. Okay, so we do the same thing. Remember, these are not axes. These are just kind of drawing guides here. In fact, I should erase those because that's not any coordinate. Theta equals pi over 4. So I just remember pi over 4 is right here. This is pi over 2, pi over 4. So here's a point that fits at pi over 4, and there's a point, 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 there's a point. But remember, if I'm looking in the pi over 4 direction, these all make, these are where r is greater than 0. However, I can go this way too. I can say, I'm looking at pi over 4 but walking backwards, and go this way. So this one here, this group r is less than 0, so these are negative numbers. So we have two different kind of regions. Let's do greater than 0 green. These are all the r is greater than 0, and then the r is less than 0. Let's do those in red. And they continue on like that. Okay? So even though I'm looking in the pi over 4 direction, I can extend the opposite direction, or pi over 4 plus pi, if you want to think about it that way. Pi over 4 plus pi. I can walk backwards as well. All right. Now, these are easy. There's no theta in this one, just r equals 6. There's no r in this one, theta equals pi over 4. What if we have a combination? Let's take a look at one of those. So, I want to graph r equals 6 sine theta. R equals 6 times the sine of theta. What is that going to look like? So I'm going to start by making a table of values here. And it's going to be, I'm going to have my thetas and my r's. I'm going to make a table. See if I can fit them all in there like that. And I'm going to speed through this because it's a little boring to watch. But I'm going to pick as my values. I'm going to say, maybe I'll even go with pi over 6's all the way up to, well, let's go 0, pi by 6, pi by 4, pi by 3, and then I'll go to pi over 2. And then I'm going to start to skip here. I'm going to say 2 pi by 3, and then 3 pi by 4. Actually, I haven't skipped any yet. And then my next one would be 5 pi by 6. And then I'm going to have to continue on over here. Well, I can get all the way to pi. And then I'm going to continue here, theta, r. After pi, we'll go 5 pi by 4. And then 3 pi by 2. And 7 pi by 4. So you can see I'm skipping, I'm reducing my resolution here just so it doesn't take so much time. Now I took the liberty to draw these ahead of time, or calculate these ahead of time, so trust me that this would be 0. No, don't trust me, verify this. This will be roughly 3, this will be roughly 4.24, this will be roughly 5.2. And sine of theta is a maximum when theta equals pi over 2, which is where we're at. So that's 1, so that becomes just 6. Now we know that sine is we're at the top of the unit circle now. Now we're going to start working our way back down. So this is going to be symmetric about here. So when I go to 2 pi by 3, that'll drop down to 5.2, and that'll drop down to 4.24. And then down to 3, and all the way back down to 0. Okay, and then now when we get in the bottom half of the unit circle, this is kind of the pi by 4 family, so this will be negative. So this is 5 pi by 4, so it's kind of over on the left on the bottom half, so we're expecting a negative y value, but it's in this family, so it's going to be negative 4.24. And then 3 pi by 2, well, that's at, all the way at the bottom of the unit, I draw a unit circle over here, all the way at the bottom of the unit circle, so that's going to be a negative 6. And then back to negative 4.24, and then to 0. All right. Now I can go over here and sketch a picture of this guy by inserting a picture. And that's in supplemental. Let's see, polar, I think. Wrong class, maybe. Yeah, Calc 2, supplemental. I thought I have some stuff. Polar coordinates there. There's a polar graph. Okay. Well, that might be as big as we'll be able to make that guy. There we go. Okay, now we're going to do, this is polar graph paper. And I'm going to sketch in our coordinates. All right. So when theta equals 0, r equals 0. So I have a point. I'm going to do this in a different color just so it's easier to see. Let's do it in green. So when theta equals 0, I'm looking in this direction here along, but then my radius is 0. So I have one green dot there. My biggest value is going to be 6. So let's set a scale here. Maybe 1, 2, 3, 4, 5, 6. I think will be right there. Let's call that 6. R equals 6 there. Just so I can scale these things. And then now when I'm looking in the pi over 6 direction, which is here, my radius is going to be 3. So this is 6, 5, 4, 3. Oh. 6, 5, 4. Why is that not letting me draw in there? There we go. So my first point is here, my second point is here. When I go to pi by 4, it's going to be 4.24. So here's pi by 4. There's 1, 2, whoops, 3, 4 and a quarter-ish. Like that. And then at pi over 3, it's 5.2, so it's almost 6. Here's my 6 line. And here's pi by 3. So 5.2 is about there. And then finally I get all the way to 6 at pi over 2. So I think here's my 6 line. All the way up here. Like that. And I remember it's somewhat symmetric about this pi over 2, right? Because I've now made it to the top half of the unit circle. My sign is going to start going down. So it's going to be 5.2, which is roughly here. And then at pi over 3 pi by 4, over here it drops down to 4.2. 5.2, 4.2, so it's roughly here. And then 5 pi by 6 goes to 3. You can see how this is tedious. So why are we wasting our time doing this? We'll see that shortly. And then the radius comes back down to 0. So far what do I have? It kind of goes out like this. And it goes like this. And then down like that. Okay, so it looks like it actually, no, that might actually be a circle. But it's sitting up. It's not centered at the pole anymore. It's centered up here. But we're not done yet. We have to keep going. 5 pi by 4 gives me a negative radius. All right, so if I look in the 5 pi by 4, so here's pi by 4. 5 pi by 4 is here. Then so I'm expecting to be drawn out here, but then I have a negative radius. So I go back along here. Oh, I've already got a point there. Let's make that point bigger, because it happens twice. Here's 3 pi by 2. I'm looking down in this direction. I go all the way up here to this. Oh, that's interesting. So the same thing keeps happening. 7 pi by 4, which is over here. Another negative radius, negative 4.24. Oh, look, that's already there too. Oh, that's this one here. So we'll make that one darker. And 2 pi, I'm looking in this direction. My radius is once again 0. So as I went from 0 all the way to 2 pi here, what I actually did is 2 complete laps around this circle. So I did 1 complete lap all the way around the circle from 0 to pi. And then I did a second complete lap. So it's important to write 2 full laps. Like that. And we'll learn more about why that's important and why we need to be aware that we did 2 laps when we start calculating areas and lengths. Because if I said how far is it around the circle, and you said, well, 0 to 2 pi, and you did 1, 2, you'd really get 2 circles here. If I said, what's the area, and you did 0 to 2 pi, same thing would happen. You'd get double the area. So you need to be aware. Your calculator won't tell you this is 2 laps. Your calculator just says this is a circle. Right? You have to be able to figure out what's going on. So likewise, I could do a another similar graph for graph r equals, what if I said 6 cosine of theta? Okay. Now I could go through and make the whole table of values, 0 to blah, 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 you know, and it's going to take me 10 minutes to write all that stuff out. But let's think about this. If I were to just sketch a graph of these the old-fashioned way, or if I graphed, this is theta, and this is r, and remember the sine graph looks something like, you know, like this. Well, what is the cosine graph like this? This is 6 sine of theta. And if I graph the cosine of this, we'll do that in orange. Well, cosine just starts up here. So cosine is always just a little bit behind, or a little bit ahead, depending on how you think about it. That's going to be 6 cosine of theta. Right? So when we make rather than making the whole same table of values, I'm going to start with that, you know, if I go back here, my values were 0, 3, 4.2, 5.2, and 6. But when it's the cosine, I'm going to start at the 6. So let's try to exploit that fact. So my table of values will be, let's make a theta, and theta and r like this. And we'll kind of see what happens. I'm going to start at, this theta starts at 0, and then we're going to go do the same thing, pi by 6, pi by 4, pi by 3, pi by 2, and then we'll go, what comes after 2 pi by 3, and then 3 pi by 4, and then 5 pi by 6, and then pi. Right, my values are going to start at 6. This is 6 up here. And they're going to drop down, so it's going to go 6, 5.2, 4.24, 3, 0, right? Because cosine at pi over 2 is 0, so I did that correctly. And then there's some symmetry there, except I start going negative. So it goes negative 3, negative 4.24, negative 5.2, and then negative 6. All right? Now we're going to do the same thing. Take a look at what this guy looks like by inserting the same picture. Oh, there it is. And we'll drag that guy down like that, make it as big as we can. If I go through and plot this one now, if this didn't make sense how I very quickly did this based on how I transposed between cosine and sine, you need to ask me about that, because this is a trig skill that's pretty important. Now in orange, let's do the same thing a little more carefully. Here's 1, 2, 3, 4, 5, 6. So when my theta is 0, I'm looking in the 0 direction. My radius starts at 6 right away. And then at pi over 6, it drops down to 5.2. So here's 6. 5.2 is roughly there. And then pi over 4 is 4.2. Here's pi over 4. This is 5. 4.2 is roughly there. I don't want to move the picture. All right. And then at pi over 3, it drops down to 3, because the cosine of pi over 3 is 1/2. So here's my 3 line, like that. And then it goes down to At pi over 2, it drops all the way down to 0. So we've got a point there. But now we continue on to 2 pi over 3, but we get a negative radius, right? At 2 pi over 3, I'm looking in this direction, but I get a negative radius all the way down to 3, which is 1, 2, 3, negative 3, and then I go to negative 4 point whatever, so here's 3, 4, 4.2 something, is roughly there. And then negative 5.2, I go to here. Yeah, like that. So now what happened just going from 0 to pi, I trace this circle here. So 0 to pi equals 1 lap around the circle. Again, your calculator wouldn't tell you that. Your calculator just tells you a picture and says, trust me. Right? But now we know that to make one complete lap of this, we only have to go from 0 to pi. Knowing how far to go in terms of theta is going to become very, very important. All right, well, that was a painful amount of work. If you ask me, we've spent, I don't know, 20 minutes or something going through this, and we still haven't really got to the good stuff. So, how can we make this easier? Right? How to make easier. We're going to look for symmetry. We're going to look for symmetry here. All right. Now, I'm going to draw, or insert another one of these polar graphs just because it's going to help you. Polar coordinates, polar JPEG. Okay, put that guy there because that's going to help us keep track of the stuff I'm going to tell you. So, first is symmetry about what we call the polar axis. Polar axis? No, it's the polar axis. Now, another way to think about the polar axis is we're going to call this up-down symmetry. Or, I hate to do this, but I'm going to do it anyway. It's kind of similar to symmetry about the x-axis. There are no x and y axes on the polar coordinates, but we're pretty familiar with this being the x-axis. It's really the polar axis or up-down symmetry. All right, so how does that work? If we can say that r and theta, the point r theta, r comma theta, is interchangeable with two other points. One of those points could be r negative theta, r comma negative theta, or the point negative r comma pi minus theta. Pi minus theta. When have we talked about that before? We talked about this when we were doing that optics problem, right? Supplementary angles. So, if we can take a point r theta and interchange it with r negative theta, so let's try that. I'm going to run out of colors here, but let's do this in blue. So, say I have a point that's here, like that. That's r theta. Well, if it's symmetric about the x-axis, that means I could go to the same r, but a negative theta. So this is theta here, But if I go to the same r and a negative theta, that means I'm going, instead of clockwise, counterclockwise direction, I'm going to go the clockwise direction. It says down here. So the same r, so I'm staying along this line, but I go down to here. So this would be the point r negative theta. Right? And if my equation tells me, if my equation will give me a curve that's symmetric up and down, r and theta must be exchangeable with r and negative theta. They will both appear on the graph. Likewise, if it's symmetric this way, I could go to, how does this work? Negative radius and pi minus theta. Well, where is pi minus theta? Pi minus theta is way back here. So way back here we have, this is pi minus theta. If this is theta. So this is theta, so this is the supplement pi minus theta. But then I go in the negative radial direction. So I'm looking at pi minus theta, but I go backwards. Oh, look where I wind up. Right there. So this could also be negative r and pi minus theta. So if that works, we're good. So let's check it. One of the first ones we did, I believe the green one, was r equals sine theta, or r equals 6 sine theta. R equals 6 sine theta. Do you remember what that looked like? I don't remember, but maybe we can learn about some symmetry. So we could say, if that works, then I should be able to stick in a negative theta there, right? So this gives me r equals 6 times the sine of negative theta. Right, but if I change it, I remember a sine is odd, so if I change the theta, that equals, does that work? I don't know. But that is the same as saying r equals negative 6 sine theta. Well, r equals 6 sine theta and r equals negative 6 sine theta, that doesn't work. So, no, that didn't work. What about the orange one we did? Let's change that to orange, which was, I believe, r equals cosine theta. R equals 6 cosine theta. And that means that r must equal 6 times the cosine of negative theta. I don't know, that doesn't look like a theta, but you know what I'm trying to say. Well, so does this work? I remember the cosine is even, so whether I go negative theta, positive theta, the cosine stays the same. So this is r equals, well, cosine just goes positive, so that's 6 cosine of theta. Oh, and that works. So the 6 cosine theta must have been up-down symmetric. Let's go back and check. Oh, look at that. Sure enough, r equals 6 cosine theta is up-down symmetric or symmetric about the x-axis. So that would save us a bunch of time if we're trying to plot this thing. So now let's do symmetry about the, I'll see if I can fit it on here. Symmetry about theta equals pi by 2, or we'll call that left-right symmetry, or the y-axis, which bothers me just as much as it did the last time, but I'm doing it anyway. Now, if that works, let's try to figure out how that works. This part we did in blue color. I told you guys the color is going to get ugly here. So that's in blue. What color do I have left to do? So we'll do in purple. Yeah. Green? No, we used green already. Deep red? Yeah, we can do deep red. All right. And this will work if, let's see, r and theta are interchangeable with let's see, r theta, our interchange with negative r and negative theta, or positive r and the supplement, pi minus theta. Okay, and that one we're going to do in red over on our picture. So we'll do some point here, we'll call this one r and theta, so 5 pi by 12, and let's do it way out here. So that we're going to make this direction theta, and this point will be r comma theta. Now it interchanges with negative r and negative theta. So if we go to negative r and negative theta is way down here. So that's down here. This is negative theta, but then we go negative r direction. So I look in the negative theta direction, but I go in the negative r distance. So that goes out to here. So that point is negative r negative theta is this point. Or I could go to r and pi minus theta, the same r, positive r still, but the supplement. And so here is my supplementary angle. Here's pi minus theta. Oh, so this is also pi minus theta here. And I go on the same radius, and oh, sure enough, there it is. So that's also r and pi minus theta. So that checks out there. Well, let's do our same tests. Let's check r equals 6 sine theta, and that should give me, let's see, I'm going to swap out negative r for negative theta. So negative r equals 6 times the sine of negative theta, and that gives me negative r equals, remember sine is odd, so if I make the sine of the negative angle is the negative sine, so negative 6 times the sine of theta. So what is that noise? Okay, so where were we here? We said that we started with the equation r equals 6 sine theta. We put in a negative r and a negative theta. We got negative r equals negative 6 sine theta, which gives r equals 6 sine theta, so that works. All right, that's good. So it must be symmetric about the left-right, symmetry, or symmetric about the y-axis. The other one, the one that was in orange, we had r equals 6 cosine of theta, and if we try this symmetry test here, negative r, negative theta, so that's negative r equals 6 times cosine of negative theta. Well, I know the cosine is even, so cosine of negative theta is the same as cosine of theta. So that gives me negative r equals, I'm trying to write small here, it's not working well, 6 cosine of theta, right, which is not the same. So that's negative r equals 6 cosine theta, r equals 6 cosine theta. That doesn't work. So that one is not symmetric in the left-right direction. Okay, let's check out cosine. Yep, sure enough, cosine was not symmetric in the left-right direction. It's symmetric about this line, but it's not symmetric about the line pi equals, theta equals pi over 2. So these symmetry tests become pretty useful they might save us some time. There's a third symmetry test that we can do. and that's symmetry about the pole. About the pole, and I'll throw in that same picture again here. And symmetry about the pole, if r and theta interchange with either the points negative r theta, negative r comma theta, or r and theta plus pi. Those are the 2 points. So let's try that again. We'll do the same deal, do it maybe in purple this time. So here I've got some point r theta. R theta. Now if it's symmetric about the pole, it should wind up right down here. Right? So negative r, same theta. This is still theta in this direction. But if we just go down here, it's just negative r and the same theta. So that makes sense. Likewise, r and theta plus pi. So what does that mean? Same r, but theta plus pi. So that means if I go to, here's theta, and then plus pi down here, so this is theta plus pi. Right, and then sure enough, there's r. So this is negative 2 points here, negative r and theta, and this also works out to be r and theta plus pi at that same point. So that would give us symmetry about the pole. Neither of our previous 2 examples had polar symmetry, and I can't think of an example off the top of my head. I do have an example, but to save time, there will be ones in the homework that are like that. The final topic that I'm going to talk about here is the topic of slope. Slope. And when I talk about slope, I'm talking about rise over run. Okay, you may say is so in general r is some function of theta. Right, we plug in a theta and then we get some r out of it. So is the slope, right, dr d theta? How is the radius changing? Little change in theta, how does the radius change? Is that slope? Well, I don't know if that works. If we look at that example again, r equals 6, right? Dr d theta, well, r is constant, so dr d theta equals 0. But I know that if I draw this, my slope is constantly changing. Right? We've done a homework problem like this where it's changing. So that can't be. Slope is not dr d theta. Right? A lot of people make that mistake. Typically we define slope, this one's getting long here, on the 11th page of notes. Define slope as dy dx. Like that. Not dr d theta. And let's take a step back here. And when we first started talking about polar coordinates, we said r equals some function of theta. But we also said that x equals our cosine of theta, right? So that equals f of theta, because r is a function of theta times the cosine of theta, right? So let's do this in color. So that's the blue part is f of theta, and then the orange part is cosine of theta. All right, so our cosine theta is really f of theta cosine theta. And then we said y equals our, I'm going to spread this out a little bit, sine of theta. So that equals f of theta sine of theta. Same thing there. So really, I'm defining x and y both as functions of the parameter theta, right? And so the other day, in class, for those of you who are in the class, we talked about how we have to be very careful about, messing up, theta t being a parameter, theta being a parameter, or theta being an angle. Now I'm saying that theta actually is a parameter. And so we always have to keep that straight. And we know that dy dx has to equal dy d theta over dx d theta. Like that. And so how do we do that? Well, dy d theta, here is y, it's f of theta sine theta. So it'll be first times the derivative of the second, which is, I'm going to write it like f of theta cosine of theta. Plus sine of theta f prime of theta. Like that. Product rule, right? First times the derivative of the second plus the second times the derivative of the first, divided by the product rule as it applies to this one. So it's going to be f of theta first times the derivative of the second, which is negative sine of theta, plus the second, which is cosine of theta, times the derivative of the first. Okay. We can clean up the algebra a little bit here, just because the negative sign kind of appears. So the formula that you might want to use looks like this: dy dx equals f prime theta sine theta plus f of theta cosine of theta. Divided by, ooh, that was horrible, f prime theta cosine theta minus f of theta sine theta. Right, same thing, I just changed the order really on the bottom. I should sign theta on the bottom, so it's a little more consistent. F prime sine, f cosine, f prime cosine minus f prime f sine. So that's the equation for the slope. All right, finally, holy cow, this is getting long. I'm going to start on page 13 here. We're going to do one example where we try to apply all this stuff. And our example is going to be r equals 1 plus the sine of theta. All right. A, sketch the graph. And B is going to be find slope at theta equals theta equals 7 pi over 4. All right, so here we go. We'll check for symmetry. So polar axis. So I know that if that works, it should go to r of theta is the same as r of negative theta. So r theta should go to r negative theta. So this is up down. Up down symmetry. If we plug that in, r equals 1 plus sine of negative theta, which gives us r equals 1 minus sine of theta, and that doesn't work. And likewise, we can try so if we put in a negative r and a sine of pi minus theta, so negative r and the supplement pi minus theta, like that. So we say negative r equals 1 plus the sine of pi minus theta. Does that work? The sine of pi minus theta, remember sine is the y value, so really that stays the same, so that becomes negative r equals 1 plus the sine of theta, which is not the same as our original function, so that doesn't work either. So neither of these worked. So it is not symmetric about the polar axis, or in other words, it doesn't have up-down symmetry. Let's check about what I will call left-right symmetry. About theta, that's phi, not theta. Theta equals pi by 2. Now, what points do we put in there? We put in the negative r and negative theta. So r theta should go to, if it's left-right, negative r, negative theta. Negative r, negative theta. Let's plug those in. So r, negative r equals 1 plus sine of negative theta. That means that negative r equals 1 minus sine theta. So that didn't work either. No. But we can also try this other option where it's positive r and then the supplement. So r theta goes to positive r and then pi minus theta. And so we'll plug that in. So positive r equals 1 plus the sine of pi minus theta. Remember the angle and its supplement have the same signs, S-I-N, sine. So that means r equals 1 plus sine theta. Holy cow, finally we got one that works. We do know that in fact this will have left-right symmetry. Okay. Now I'm going to plot this. So make a table of values from 0 to pi over 2, because I know it goes left-right. Since I know it has left-right symmetry, so I'm going to plot values from only negative pi over 2 to pi over 2, because whatever I get on the right side is going to also happen on the left side. So we'll make a little table here. Actually, we'll make a table on the next page. So we'll say from theta goes from negative pi by 2 to pi by 2. And let's make a little table here. So we have theta and r. Theta will go negative pi by 2. And we'll go negative, what's the next one? Negative pi by 3 is the kind of next one that we work with. Negative pi by 4. Negative pi by 6, and then 0, and then pi by 6. Pi by, after it is 4. Pi by 3, and then all the way up to pi by 2. All right, and the function, as I recall, is r equals 1 plus sine theta. Like that. Well, the sine of negative pi by 2 is negative 1. So that will give me a 0 there. This is pi by 3 is like 0.866, right? So that leaves me with a 0.14. And then the next one will go to, let's see, pi by 4 is 0.707, so let's just call it 0.3-ish. And then pi over 6 is a half, so 1 minus that is, or 1 plus a negative a half is 0.5, and then this goes to sine of 0 is 0, so that's 1. And then going in this direction, pi by 6 will be 1.5. So I'm adding the sign now, and then it's 1.707, and then 1.866, and finally 2. And if you struggle to do this because you don't know your way around the unit circle very well, well, you need to know your way around the unit circle better. Finally, we can draw a picture of this thing. Holy cow. JPEG. Thank you. Okay. We'll slide this over here, make it a little bigger. We'll do this in, what's the color we have? How about light blue? Sure, what the heck, light blue. Negative pi by 2, my radius is 0, so I start right here at 0. And then negative pi by 3, so pi by 3 is right here. The radius is 0.14. The biggest radius I ever have is 2, so I'm going to call this 2 way out here. And then that makes this about 1. So 0.14 is way in here. Ish. And then negative pi by 4 is 0.3. So this is negative pi by 4, so we'll make that 0.3 there. And then negative pi by 6 is 0.5, so that's there. And then at 0, my radius is 1, so where is 1? Right there. And then at, let's see, positive pi by 6, which is right here, my radius goes all the way to 1.5, so I'm at like there. And then pi by 4 is 1.7, so I go out to here. 1.866, so I go to here. And then at pi by 2 it goes to 1. Now why did I only have to draw this much? Because I know it's going to look the same at the other side. When I sketch this guy in, try to make some smooth kind of line that connects all this stuff, it kind of looks like this. And by symmetry, I know that it's also going to do the same thing on the other side. So how's that for symmetry? So this thing is what we call a cardioid, and because it looks a little bit like this one doesn't look much like a heart, but it looks like an upside down heart. So that's what that is. Now, for the sake of time, I'm not going to do the slope because this has gotten way too long. And for the slope, remember, we just have to plug it into this equation here. All right, so at the slope, we're looking at 7 pi by 4. Okay, and I think you'll find if you do that, that the algebra works out pretty nicely. A bunch of numbers cancel out, and you wind up with a pretty clean number when all is said and done. So I'm going to write that on your own. Find slope at 7 pi by 4. Where is 7 pi by 4 then? 7 pi by 4 is right, it's almost at pi, so it's over here somewhere. Okay. Is that what it was? It was 7 pi by 4? Oh, 7 pi by 4 is over here, right down here. Right, it's almost 2 pi. So somewhere in here we're going to find the slope. All right, that's it. Sorry it got so long, but it's kind of a complicated topic. We will talk about it in class.